All right, hello. Welcome back. In this module, we will be talking about the dynamics of system of particles. So you can imagine a collection of particles either fixed in relation to each other, and that would make, for instance, a rigid body, or in a very general case, just a collection of a bunch of particles with mass and everything, and we want to analyze dynamics of that, as in we want to see how the interaction between forces and kinematics take shape. So in this module, I think there's going to be maybe 5-ish videos, and we'll be talking about the translational motion, rotational motion, and also look into the concept of work and energy. All right, to begin, let's first look at the translational motion because that is the easier part. So here is the general setup that we will be using throughout this module. So we have a collection of bodies or a collection of particles. We have, let's for now say we have n particles. And each of them have the mass mi, and there is some external force acting on it. So Fi is, well, resultant. We can imagine all forces, all external forces acting on that particle is summed to be Fi. Sum of all external forces, and there is an interaction force between each pair of body. Ij, little Fij is force of body J on I. So we are looking at an inertia frame with a fixed base point O for now. So O, X, Y, Z is an inertia frame. Inertia frame. Inertia frame. And I think the last bit is this RC is location of the center of mass. So let me write it this way. Center of mass, often I abbreviate it as COM, and its location is 1 over m. M is the total mass, or I can write it here. M equal sum of mi. No, I'm going to write it over there. Here. M equal sum of mi. I equals 1 to m. 1 over m, sum of ri, mi, sum over I. So this is the setup. We know a bunch of particles, where they are, how they are interacting, their forces, and center of mass. So we know for just one particle, so for particle I, we know the Newton's second law. We have, let me see, what is the best notation to use? We have mi ri double dot equals sum of forces, so external forces plus sum of all internal forces, ij. All j particles exert some force on I, and we are summing those, and that is the total force. So that is for one particle. I can, for the system, I can sum all of them. So sum So it is called equation of motion. So this is equation of motion, or sometimes I abbreviate it as EOM, sum all EOMs. So what I have is summation of all particles, MI, RI double dot, equals the summation of that is summation of all external forces plus summation of all internal forces. So the good thing here is that if you notice, well, that is the Newton's third law. So I have Newton's third law. It's the law of action and interaction. So Fij is always equal minus Fji. So when I'm summing all these internal forces, there's always going to be some force that is going to be cancelled out by the reaction of it. So this thing is actually 0, and what we are left with is sum of mi ri double dot equal sum of all external forces. And here is where the definition of center of mass comes in handy. So from definition of center of mass, I can write mRc equal sum of I ri mi. And if I take the second derivative of this, d over dt d2 dt2, what I get is the same acceleration. So in the end, mRc double dot equal sum of all external forces. So I don't have OCD, but sometimes these things annoy me. That's bad. Okay, what it means is we can gather all mass at COM, and then the motion of COM is MAC equal sum of external forces. So I can clump everything in my entire system into one point and look at the kinematics of that. That's very useful and very powerful. Doesn't matter how the body is how this collection of bodies are moving relative to each other. I can always look at just the center of mass. That's good. And let's also take a look at momentum. So linear momentum or translational momentum. So it is defined usually with P. P is defined as mass of a particle times velocity of a particle. I'm writing it as R dot I. So it is also a vector quantity. And what I can do is find the linear momentum of the whole system, so P, and I can add all Pi to get the momentum of the entire system. What I have is Mi R dot I. Now taking a derivative of that, what I have is P dot of the rate of change of linear momentum of the entire system equals mi r double dot I, which we gathered is this Fi. Oh, that's very ugly. Sum of Fi. So this is called the principle of, well, not yet, but it's the relation between the rate of change of momentum and the external forces. You can take integral of that over time, and P2 minus P1 is integral of sum of Fi dt. This one is called the principle of impulse and momentum. This is impulse, and this one is change in momentum. So, principle of impulse and momentum. And the last thing, looking at this equation. So if sigma Fi is 0 in any direction, so we are dealing with a vector equation. So you can look at any axis and write your equation along that axis. So if in any direction the sum of forces are 0, sum of external forces is 0, means P along that axis remain constant along that direction. So it is called the principle of conservation of momentum. Principle of conservation of momentum. So, let's see if I have anything else I need to talk about. I don't think so. So it's all good. So we have covered the translational motion. In the next video, we will be talking about rotational motion, which is significantly more fun, I would say. All right, until then.